We've just learned about null spaces, and now we're going to take a look at column spaces. What is a column space? Well, it is the set of all linear combinations of the columns of matrix A. So keep in mind, matrix A is comprised of vectors, and the column space of A is the span of those vectors. So this all linear combinations of the columns of A should look real familiar to, because we've talked about that before, and that just means it's the span of those columns. So again, we keep working on these same concepts over and over, and they might look a tiny bit different, so it's difficult to keep everything straight, but we know that if we can write a linear combination, it's in the span, and that's what we're looking for, is the span for the vectors in matrix A. Another way we could write this is that the column space of A is equal to all B, such that B equals AX for some X in Rn. So again, it's every single value that provides us with a solution, which would mean that it's in the span. A theorem in your textbook says if A is an m by n matrix, the column space of A is a subspace of Rm, and we're actually not going to prove that one because we know, based on a proof, I think we proved it in a previous video, either that or we just talked about it, that the span of vectors is in fact a column space of Rm. So we're not going to prove that, but just know that is a theorem in your text, that the column space of A is a subspace of Rm. Here's a great practice for us, not only in null space, but also in column space. So we've got one vector A, one matrix A and one vector U, and I'm asking if U is in the null space and if U is in the column space. So this would be a good practice to help us to know exactly how to go about solving these. So as a reminder, if we're looking at null space, we're saying that A times U would have to be 0 for this to be true. So that's pretty straightforward. All I have to do is do some multiplication. 2, negative 6, 12. Make sure you multiply in the proper order. Negative 3, 9, 9, 0, 0, 1 multiplied by vector U, which is 3, 1, 0. That's going to give me 6 plus negative 6 plus 0. And then negative 9 plus 0. And then 0 plus 0 plus 0. And I end up with 0, 0, 0. And because this is the 0 vector, which is what I was looking for, then I can say, therefore, U belongs to null A. So now let's switch gears and talk about the column space. For the column space, we're going to take A and augment it with U, and then we're just going to do row reduction and determine if it's a consistent system or inconsistent. So if the system is consistent, then U would be in the column space of A, and if it's inconsistent, then it's not. So that means I've got 2, negative 6, 12, negative 3, 9, 9, 0, 0, 1, augmented with 3, 1, 0, and I'm just going to do my row operations. So again, there's really no right or wrong way to do your row operations. I'm just trying to get it to the point that's either in reduced row echelon form, or I find out that I don't have enough pivots and therefore it's inconsistent. So the first thing I'm going to do is I'm just going to reduce my first row by 1/2. Oops, that is not 4. Half of 12, still 6. And then I'm going to reduce my second row by negative 1/3, so that gives me positive 1, negative 3, negative 3, negative 1/3. And 0, 0, 1, 0. So it's pretty clear I'm going to have a pivot here, and it looks pretty clear I'm going to have a pivot here probably, but let's go ahead and keep going. if I do another row operation, I'm going to keep this 1, 3, 6, 3 halves. And then I'm just going to subtract the two rows. So 1 minus 1 is 0. Negative 3 minus negative 3 is 0. 6 minus negative 3 is 9. 3 halves minus negative 1/3 is 11/6. And this is 0, 0, 1, 0. And then hopefully at this point you can see that there is no pivot in the second column, and therefore this is inconsistent. You could obviously keep going, and if you kept going you would end up with a 0, 0, 0, 0. But it's really not necessary, because once I got to this point it's pretty clear that there are not enough pivots. So because this is inconsistent, and then therefore U does not belong to the column space of A. Here's another practice for us to try. This one asks us to find a matrix A such that W is equal to the column space of A, and then it gives us this matrix W, which is sort of defined in a weird way. But this is actually a fairly straightforward question. I know that W can be rewritten as a linear combination. So I can say that this is A times 4, 1, 0, plus B 2, negative 1, negative 4. And then of course A and B are real numbers. And so essentially what I'm saying is this is the span of 4, 1, 0 to negative 1, negative 4. But I still haven't answered the question, because the question says find a matrix A. So what they want me to do is find a matrix A. Well, no problem. A is then 4, 1, 0, 2, negative 1, negative 4. There's my matrix A that exists such that W is equal to the column space of A. Here's a great practice for you to try on your own. So I would like you to try this one, and when you're ready, press play to see how you did. If we're not quite there yet, that's okay. You can just wait and I'll go over it with you. All right, let's take a look. I'm asking you to find both a non-zero vector in the column space of A and then one in the null space of A. And you'll find that the non-zero vector in the column space of A is any one of these columns written as a vector. So I'm going to choose, say, 4, negative 1, 6. That is a perfectly good solution. I could have chosen any one of those columns and that would all be the correct solution. For the second part, a non-zero vector in the null space of A requires me to take A and row reduce it and augment it with the 0 vector. So I'm going to take 1, 0, 3, 4, 0, 1, 4, negative 1, 0, 2, 0, 6, augmented with the 0 vector, and do some row reductions. So I like my first row. I've already got a 1 and I've already got a 0. And I actually like my second row because I have a 0 and a 1. So far, I've got a pivot, and I need to turn this guy into a 0. So let's take 2 times row 2 and add it to row 3. So I get 0, subtract row 3. So 2 times 1 is 2, minus 2 is 0. 2 times 4 is 8, minus 0 is 8. 2 times negative 1 is negative 2, minus 6 is negative 8. And then, of course, 0. Continue with my row operations. So my first column's great, my second column's great. I'm going to leave the first and second rows exactly as they are for now. And in that last one, I'm going to take it times 1/8. So that gives me 1, negative 1. and then I'm almost where I want to be. I've got a pivot, I've got a pivot, and I've got a pivot, but what I don't have is I need a 0 and a 0. So let's keep going. That's going to give me first row. I'm going to take my third row times -3 and add it to my first row. So I get 1, 0, 0, and then 3 plus 4 is 7, 0. And then for my second row, I'm going to take my third row times -4 and add it. So I get 0, 1, 0, and then that's +4 plus -1, so that's +3. And then this guy I didn't do anything to at all. So what am I going to do from here? Well, I know that my solution is that x1 is equal to -7x4, and because obviously x4 is my free variable, and so that's the only one I should have here. And then x2 is equal to -3x4, and x3 is equal to 1x4, and x4 is free. So really my solution here, if you'll recall, is that I can write it -7, -3, 1, 1. And from here, I'm looking for, again, a non-zero vector. And so what that tells me to do is essentially come up with some x4. So whatever x4 I want, and then multiply it. So let's just say x4 is 2. So a non-zero vector in the null space of A would be, if I turned this into a 2, which would give me -14, -6, 2, 2. So that's one of the many, many solutions. I could have a solution for any value of x4 that I chose. One last practice for us. Again, 2 parts, so press pause, try both parts of this question, and then press play to see how you did. So the first thing to talk about here is A with respect to U. So the first question says, is U in null A? And of course, we already know how to do this. This is 1, 0, 4, 0, 0, 1, 2, 0, 0, 0, 3, 1 times 2, -1, 3, 4. And I'm essentially asking, is this 0? So I would get 2 plus 0 plus 12 plus 0. And do I even need to continue? Because that's 14. And so this is not equal to 0. And I could continue. I would get 0 plus -1 plus 6 plus 0, which is 5. And I would get 0 plus 0 plus 9 plus 4, which is 13. Again, not the 0 vector. Therefore, U does not, whoops, wrong notation, U does not belong, wow, to null A. There we go. The second part of this question says, could U, the vector U, be belong to the column space of A? And hopefully it's very clear that this answer is no, because we talked before about the column space of A. Obviously, that would be these vectors. So Could U, which is in R4, be in the column space of A? No, because column space of A, is a subspace of R3. Let me get rid of those little markings now. So let's move on to the next one. Is V in the column space of A? So here's V. They're asking, is this in the column space? Well, are any of these that exact column? No. So no. These columns, none of those match column that is the vector V. So that's a big fat no. So the second question says, could V be in the null space of A? So good question. What do we know about the null space of A? Well, the null space of A is a subspace of R4. So again, the column space of A is a subspace of R3, the number of rows. The null space of A is a subspace of R4, the number of columns. So could V be in the null space of A? And again, this is a no, because it has to be a subspace of R4, and obviously V is in R3. I want to sort of rewind back to something that we've talked about before, and that is linear transformations. That's not going to be our focus in this section, but it was in the textbook, and I just wanted to make sure that I brought it up in the videos. So we have talked before about a linear transformation from a vector space V to a vector space W. Now, previously we did not talk about a vector space, but essentially what we talked about was that we had some set, and that linear transformation is just a transformation onto another set. So this is a function. So if you'll recall, a linear transformation, and again we're looking at it from a vector space to a vector space, which is not what we did previously, is a rule that assigns a unique vector tx to each vector x. So again, x, tx, again a function, such that the transformation of the sum of vectors u and v is equal to the transformation of vector u plus the transformation of vector v. And again, for all u and v in the vector space V. And that the transformation of some scalar times vector u is equal to the scalar times the transformation of vector u. So that was just our same definition that we talked about before, this time applied to vector spaces. A couple of new terms for you. Null space of T is called the kernel. And again, we're not going to focus on that in this lesson, but you will see kernel again throughout your mathematical education, so I'm going to let you know now. The null space of T is called the kernel, and again, here is the mathy definition. And essentially we're just saying that if, just like before when we talked about the null space, we said AX was equal to 0. So notice I'm saying all of the vector u's in the vector space such that the transformation of vector u is equal to 0. So that is called the kernel. And then the range, again, just thinking back to this transformation, this is our domain and this is our range. The range of T is the set of all vectors in W of the form Tx for some x in V. So again, that's the range, what is going to map back to our original x.